assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this example, we have a square loop here that's sitting in a uniform constant magnetic field. We're allowing this loop to spin about this vertical axis here. So it starts off where the surface normal of our loop is completely parallel to the magnetic field, and then it spins 90 degrees like this to where it's completely perpendicular. So this would be a view from the side, the second picture here. So we go from a situation in which there is magnetic flux to a situation where there is no magnetic flux. So given that we know the area, the number of loops in our coil, the resistance of our coil, and how much charge flows into it, we want to determine the strength of the magnetic field in this time. Okay. So the first thing to remember that often is for these induction problems is that the induced EMF is equal to the change in the magnetic flux or the change in time. This is known as Faraday's law of induction. We often put a negative sign on that. So our change in flux can just be written as the final flux minus the initial flux, where our final flux is going to be 0 in this case, because we go to a situation in which our surface normal, which point like this, is perpendicular to the magnetic field, right? If the magnetic field's into the page in my drawing. So no flux there. And in the initial one, we will have flux. Remember, flux is just the strength of the field times the area times the cosine of the angle between the surface normal and the magnetic field, which in this case, they'll be perpendicular at this initial time. So the cosine of theta is just 1. We're just dealing with B times A. So our total change in flux then is just going to be minus B times A. And if we plug that into our Faraday's law up here, we'll have that the induced EMF is equal to minus B times A. So just have B times A over delta T. All right. So we have more unknowns than we'd like at this point, right? But we're going to get rid of them by virtue of the fact that we have some more information here. Specifically, we have information about the circuit, right? We know what the resistance of our circuit is, and we also know how much charge ends up flowing into it from this spin. So the law that we always come back to for circuits is Ohm's law, right? V equals IR. Or in our case, our voltage is just going to be our induced EMF. So we'll have E equals IR. So we have a way to relate the voltage to the resistance, and we know the resistance, so we could get rid of our induced EMF here in this equation. But we're still left with I, right? But if we recall, the current is just going to be equal to the charge over time, right? So if we know that, calling it Q here, we can substitute that in to Ohm's law, and we'll have Q times R over delta T. And if we substitute that in, Ohm's law, for our induced EMF over here, we'll have Q times R over delta T equals B times A over delta T. So we've eliminated E, and we can also see that time is going to be completely irrelevant because there's a delta T on both sides. We can cancel it out. So in the end, all we have to do to find our magnetic field B if we have QR times or equals BA, is just divide both sides by the area. And we're left with B is equal to Q times R over A. Now we forgot one thing here. This would be for a loop with a single turn in it, right? So when we were writing out our expressions for the magnetic flux, we needed to add in the flux through every loop, right? BA is just going to be through a single loop. So really our initial flux should be N times B times A. Then the change in flux would be minus N times B times A. And then we'll just follow that through our whole problem here. So we'd have another one here for our induced EMF. And then we'll have one here. So actually at the end, we'll divide by N and A. There we go. So we'll end up with QR over NA. Okay, so now we're in a spot where we can just substitute all our values in. We have Q, N, R, and A, and it looks like they're all in the proper units, standard units. So if we plug those values in, we will get a strength of 0.16 Teslas for our magnetic field.